Okay.
So Marco is from the University of Bergen, and Marco will talk about on the existence of certain APN function over F2 to 3 times M. Please, Marco, start your talk.
Thank you. So this work is a joint work with Daniele Bartoli, Olga Polverino, and Ferdinando Zullo, and we investigate the existence of certain APN maps that are that comes from a recent construction. And let me start with some notation and basic definition that I will use along the presentation. So we are focusing on a finite field with 2 to the n elements, and in particular we are studying some vectorial Boolean function where that are function defined from finite fields with 2 to the n element into a finite fields with 2 to the m elements. And in particular, we focus on the case when m is equal to n, and if this happens, we can represent our function as a univariate polynomial of a degree at most 2 to the n minus 1. And among these polynomials, there are a particular class of polynomials that are called linearized polynomial or Q-polynomial, that in which we focus. And a Q-polynomial is over the field F2 to the m is defined in this way with this kind of representation. So the power of our variable x are power of q, and the coefficient of our polynomial is in the field of degree m, the extension of degree m, and I will denote with this symbol L of mq the set of all q polynomials over this extension. One of the cryptographic property that usually we study for vectorial Boolean function is the differential uniformity that is defined in this way. So we are interested in the maximum number of solution of this equation where we take A different from 0 and B an element of our field. So we study all for any of these equations, the maximum number of solution is called the delta differential uniformity of our function. And for application in cryptography, we would like to have a low differential uniformity. So the optimal case will be delta equal to 1. In this case, the function is called perfect nonlinear or planar. In other setting are called also planar. But for the even characteristic case, we cannot have this kind of function, since if x is a solution of this equation, also x plus a is another solution of the equation. So the minimum value that we can obtain in characteristic 2 is delta equal to 2. And in this case, the function is called almost perfect nonlinear or APN for B. So it's important to construct family or class of this kind of function that can provide us APN function. There are some known families of APN function. The first example are the so-called power function or monomial function that are given by a polynomial, a monomial that is x to a certain power d, and we know these are 6, and it is conjectured that this table for the monomial family is also complete up to a certain equivalence relation, the so-called CCZ equivalence. And we can see that, for example, for the goal function, whenever we consider an exponent of this form, 2 to the I plus 1, this construction provides us an APN function whenever the element, the integer I is coprime with the degree of our extension f2 to the n. There are also some known so-called polynomial family that provide us some APN function that are not CZZ equivalent to the classes of power function. And more or less, these are 15 up now, depending on how we are counting them. And we can note that among these, we have some family that give us a specific condition on the coefficient involved in the univariate representation. Like for DeCifris class, we have that whenever we consider this coefficient a primate element of our field f2 to the n, and with the dimension and the integer involving in the exponent of our monomials satisfying this condition, then we have an APN function coming from this family. Besides, there are other constructions, like for example, the function, the class f3. We can see that the condition of the existence of an APN function coming from this family is based on some existence of certain polynomial. Like here, we can see that this construction provides us an APN function when we are able to find a polynomial. So C, the coefficient C should be in such a way that this polynomial doesn't admit any roots of for which x to the q plus 1 is equal to 1. So when we have this kind of construction, is important to understand whenever we can obtain for any extension that we are considering where we can define this function, if we can obtain an APN function coming from this family. For example, for the function family F3, there are a couple of works that have investigated the existence of the APN function coming from this construction. In particular, it was proved in 2013 by Bloomberg that for any extension where we can consider this this kind of construction, we can obtain an APN function coming from this one. A similar function is a recent construction by Taniguchi that consider this polynomial here, given here, and this function is APN whenever we consider U is a primate element, but A and B must satisfy this condition on this polynomial, so we cannot have any roots of this polynomial when in the subfield FQ, and the existence of this function are guaranteed thanks to a result by Elliset and Kolosha about this kind of polynomial. And in fact, we can see that considering A equal to 1, we have a number on about how many B we can have for which this polynomial satisfy this condition here. So let's move to our work. Recently, it has been introduced a new construction in the beginning of this year, and we have that this polynomial given in this form that is defined over an extension of a defined field with 8 elements. This kind of polynomial provides us with an APN function whenever we can have an element mu in this extension for which the norm of this element is different from 1, and such that this polynomial, this linearized polynomial, is a permutation polynomial for over our field F2 to 3 times m. So in their work, Lee et al. Didn't study the existence of this kind of polynomial. They were able to perform some computation for m up to 9, and they showed that for m up to 9, it was always possible to find an element mu for which this condition is satisfied, and so we can have an APN function coming from this construction. In their work, they left this open question. So when they were questioning about if there exists for any extension M an element S and an element mu for which we can have an APN function from this construction. So we started to focus on this linearized polynomial for understanding their property. And we started from a general result given by Polverini and Zullo about this kind of polynomial f, that this linearized polynomial defined over an extension of degree m times t of the field fq. If we consider sigma is an automorphism of our field that has order m over the subfield fq to the m. So then we can associate a polynomial, a q to the m polynomial to this polynomial f that is given by this polynomial representation, for which we obtain that f can be written as g composite with our automorphism sigma minus x. So, and also another polynomial that we can consider as always associated to f is the polynomial h that is given by g composite with sigma. So using these two polynomials, we can have some condition on the dimension of the kernel of our linearized polynomial f. In particular, with the polynomial g, we can give an upper bound on this dimension that is given here in the equation 2. And while we can use the polynomial h for determining the exact value of the kernel of our linearized polynomial f, studying the kernel of this map where h to the m is means that we are composing h m times. So from this result, we can immediately see that for our polynomial, where we have that sigma is represented by 2 to the power of s, and t is equal to 3 in this case, then we have that for this kind of linearized polynomial, the dimension of our kernel is at most 3. And while for the case when mu is equal to 0, we know immediately that the dimension is given by the great common divisor between 3 and s. And for if mu has a norm equal to 1, the upper bound is 2. Then we also show that the following properties. So whenever we consider integer s for which the sum of s and m is also coprime with the degrees of our extension, so with 3 times m, then for any, if we need to count the number of element mu having a certain norm equal to alpha, for which this polynomial is a permutation, we can just count the number of mu for which we have the same, these have the same norm alpha, and for which the kernel is equal to 2, and the number of mu for which the dimension of the kernel is equal to 3. So we can see that this proposition gives us a sufficient condition for the existence of an element mu with a norm different from 1, for which this polynomial is a permutation. We don't need to construct a permutation polynomial, but we need to check if there exists an element for which the dimension of the kernel is at least 2. So, and in particular, here I have, if we have some condition on the dimension of our field, then we can use the result by Polverini and Zullo for studying the polynomial h. I can report the condition that we are on the dimension are given this table, but I don't want to go into the details. I just summarizing from this result, we obtain the following existence result. So whenever we consider an integer s for which s plus m is coprime with 3 times m, then we are able to find an element mu with a norm different from 1, for which the polynomial, the linearized polynomial f mu is a permutation under the condition of given here. So for example, when m is divided by 3, but not by 9, we have that for any element s coprime with m, we can obtain a function coming from this APN, this construction, an APN function from this. So with this result, we already obtained that we can define infinite extension where we can find this kind of APN function. But we want also to understand if it was true for any extension. So let's if we didn't want any restriction on m, so we focus on the case s equal to 1. In this case, we change our approach and we start using some algebraic varieties. So let us consider q equal to 2 times m, 2 to the power of n, sorry, and we can starting with this observation, we see that the number of mu for which this polynomial is a permutation can be seen as all the element in our extension that cannot be written as this rational function. So we started looking at how many of these to the value set of this rational function, and for doing this, we consider the following curve. So we consider the curve given by this equation, and we note that we can use the number of rational points in this curve to give a lower bound on the number of elements mu for which this linearized polynomial is a permutation. Indeed, we obtain that if our curve CS contains n rational points over fq to the 3, of course, this kind of rational point that we are looking at rational point for which both x and y are not 0. So we can obtain that we have at least this number of value mu for which this is a permutation. So we needed to understand, to estimate this number of points in this curve. However, we can note that the degree of this curve is high, so it's not possible for us to study directly this curve. So we consider this kind of this change of variable, let's call it like this extra equation. So we can see that any element in fq3 can be represented in this way, choosing a basis of this extension over fq. And we consider the following variety given by this equation. It's just so we can start to we can see that the fq rational point of this variety are in objective relation with the rational point of our starting curve. So we can study this variety for give a lower bound on.
Mark, 1 minute.
Yeah, so just cut. So we studied this variety in just in reality an equivalent variety to this, and we were able to show that we have an irreducible component in that is fq rational point, and using some estimation, the Langevin theorem, particular with the estimation done by Carrefour and Matera, we were able to obtain our last result, that is for any dimension m, for any extension m greater than 3, we can obtain a permutation polynomial coming from an element mu satisfying this property. So we have always this kind of APN function from this construction. So thank you.